So I'll stand here and hope it. Some people have sound somewhere. Yeah. Anyway, getting back to your thesis. Yeah. Okay.
There is the camera.
Ah, yeah. Good. So getting back to the thesis, it's about general intelligence, and you mentioned that in connection to human intelligence. So I'm not so sure that general intelligence and human intelligence is the same thing. So are we that general? And especially if you look at different animals, they are intelligent in some way, very good at some things and bad at other things. It seems that humans are bad at very few things and good at most things, but there are also things that we don't seem to get. So my question here is: are we really generally intelligent, or are you looking at something else? Yeah.
That's a good question. And once again, Antonio, can you confirm that you can hear us? Can you hear me now? Yes, great. Thank you. So very interesting question, I think. I think general intelligence is really something that can be seen on a continuum. So I would actually argue that some kind of, I don't know, single cell organism can be intelligent in the sense of being able to do habituation that we discussed 6 years ago. Some flowers, the mimosa, can, for example, do habituation. So I would argue as long as there is, at least how I see it, as long as there is a learning principle that can be observed, I would argue that it's generally intelligent. So that would be general in the same sense of, maybe you could call it transfer.
Okay.
Like that. But of course, it's a continuum in the other way of like human level or not human level. And yeah. Do you have an example of something that is you think is generally intelligent that is not a human being?
No, but you could imagine problems that an artificial system could solve that we can't do. And of course there are problems like that we can do in principle, but in practice we can't. So that's why we're using computers for things anyway.
Yeah.
So maybe they're not always intelligent, but I mean the large combinatorial problems that we could solve given time, but we don't have that usually. So that's actually related to another thing, and that's whether, I mean, you're looking at principles here, but how important to you is it that things will work for real, in a sense, that the problem can be solved in general somehow using these systems, or that they are practically useful. As someone working with robots, of course, I'm very interested in this connection to the real world, and how easy this is to use. So how much is that a factor to you? I realize it's not that important to this work, but just the way you think about it.
So would one example be that if I let's say that some kind of control theorist in Lund solve some kind of learning problem, but call it something else and solve it in a completely different way. Is that something that you ask if that would be an example of not implementing the principle of operant conditioning, for example? And I think your question is if I still support that approach or something like that?
Yeah, not really. More about the sort of the feasibility of using things for real rather than in principle.
So things for real would be, for example, this vacuum cleaner robot that has some kind of pre-training.
Yeah. For instance, which can be a trivial thing, but anyway, whether that is relevant to your thinking about intelligence.
So short answer, yes. And I think as we, for example, combine NARS with this object classifier is one example of where we can do, how to say, reasoning or learning on something that comes out from other models. So I actually think it's the future of AI and AGI to really combine systems like NARS with these other types of data-driven system or like pre-trained models, so to speak. And one way to look at it is that, as I see it, is that a lot of the AI that we see is what I would call more similar to phylogenetic adaptation, in that they are trained before they are born, then they are born, and then they can use all of that as part of the interaction, exactly as we can use a lot of the things that were available when we were born. So I think it's interesting analogs you could observe there between phylogenetic adaptation and the kind of models that we have so many of currently, and combine those with these NARS-like systems.
Now, so related to this, you call this machine psychology. So what's psychology about it?
Good question. No, but to say really what I think is that I think psychology needs to be more what I would call scientific. And one way to do scientific psychology is to be clear that it is a science about ontogenetic adaptation. Another way to say it is that psychology is about the science about interactions between organisms and the environment. So it's a particular way to define psychology. The reason why I chose to say learning psychology here was that it's, let's call it, an established framework that I can use to, show my thesis. But just one small example is that I think what I call learning psychology is much more general than what other people might call that learning psychology is just one small piece of the entire psychology puzzle.
Yeah. So the reason I was asking this is again the role the human plays in your theorizing here. So we'll get back to your empirical studies later on, but those are specifically human tasks in a sense. So, of course, calling something psychology or machine psychology, it seemed to imply that you're interested in mimicking human ability rather than intelligence, regardless of human ability. So I'm not sure you agree on that, but that's the way I read it.
So I think the term adaptation is very important. So I would define intelligence as a form of adaptation. So an adaptation is everywhere in the universe, so to speak. So that's what I'm interested in.
Yeah, great. So this is just to warm up. We'll get to the details. Yeah. So now another more general thing here. This is, of course, for me, time travel, going back to the era of symbolic AI. That some people think is behind us. You're obviously not one of them. But to many, it would perhaps be surprising to work on this kind of symbolic systems today, where everyone else is doing large language models, and especially since you ground your work in a sense in operant conditioning. One would expect there to be a lot of talk about reinforcement learning algorithms and so on, but none of that is in your thesis. So I wonder whether you have sort of some general motivation for taking this path towards artificial intelligence.
Do you remember what your first question was 6 years ago?
No, I have no idea.
You said, why take an old theory about intelligence and AI and combine it with an old theory of psychology?
Yeah, so you have 6 years to think about it.
Yeah, I think it's the same question again.
Yeah.
So to start with, I think so one can ask then, is NARS a symbolic AI system or not? So what does that mean? Personally, what I would associate with symbolic AI is also these types of, let's call it, mechanisms like search, for example.
Yeah.
And all of those are examples of what requires an assumption of sufficient knowledge and resources. So it's not the symbols in themselves that I think has been problematic, but rather, yeah, for example, some other methods there. And also, I think it was clear in my presentation that the meaning of a symbol for NARS is very much dependent on its experience. And I would assume some kind of symbolic AI assumes that the meaning of a symbol is in relation to something out there. So that's two big differences, I would say. Then I think you said something. What you had a question about operant conditioning. So I can answer why use that. I'm not an expert on reinforcement learning. Det hörs väldigt väl om man säger det. So I'm not an expert on reinforcement learning, but it seems to me like a lot of it is about some kind of maximizing some utility function or something like that. And to me, that looks like a misinterpretation of what Skinner was talking about. And it's very common, I think, in contemporary AI that people talk about this, for example, online adaptive control and this kind of stuff. And that's much more what I think Skinner way of talking about reinforcement or operant conditioning is about.
Yeah.
So I think Skinner's theories from the 1930s has become very even more useful now. I would say that the biggest misinterpretation is this thing that, as I described, operant conditioning is an effect. It's a functional relation rather than some kind of, I don't know, association or structure.
Yeah. And
I think a lot of other type of reinforcement learning assumes something like that. So I think it's a big value in looking at learning, for example, as a change in behavior due to regularities. And you can look at a lot of cognitive phenomena in that way.
Yeah, I absolutely agree. And I think the way people have sort of interpreted Skinner's work is not really correct. On the other hand, when you describe operant conditioning as this three-part continuously, it seems that the discriminative stimulus gets a lot of work.
Mm-hmm.
Nearly all the work, I'll say. So if you would map your system onto the different parts of sort of operant conditioning model, if we call it a model, where does the different parts of the NAS together with everything else you're using, where does it fit in? Or is this just a way of looking at how you use the system?
Very good question, I think. And so to start in the middle, so you talk about the three-term continuously, like stimulus, response, consequence. So in the middle, we have the response. So as I would describe response, on the simplest level here is that everything that I called operations in the presentation, like selecting left or right, for example, that's an example of a response. It can be triggered by motor babbling, for example. So that wouldn't be a case of learning. So it's just a reaction, like a biological reaction, like that. If we have a situation like, for example, it's something green to the left, that could function as a discriminative stimulus. And the consequence that was G would function as a reinforcer. if we had G exclamation mark.
Yeah.
So G is a goal. So technically, when we as researchers write G exclamation mark, that's what's called an establishing operation, which is something some people call that the fourth term in the three-term continuity. So basically, an analog if water is the consequence, that if we water deprive the system before, that would be an analog to G exclamation. So that's one kind of mapping between these four terms: establishing operation, discriminative stimulus response, and consequence or reinforcing. I didn't talk about the punishers.
No.
I haven't written about it, but in open source applications, there is something called negative goal handling.
Okay.
Goal handling that can be used for that.
Yeah, I don't think that matter very much, because that's kind of much less general. I mean, in animals or systems that handle punishment and threats that are not really related to anything else. But anyway, let's see how. No, you talked about a possible third term here, but do you know about the occasion setting literature?
Location.
No, occasion setting.
Yeah.
Because when you don't mention it at all in your thesis, and I would expect that you would, especially when you get to relation and frame theory, because many people try to address those kinds of relation learning with occasion setting. So I would like to know if you have any comment on that, or
yes,
if it's related to what you do, or if it's distinct.
Yeah, I think it's more than a year ago. I said to my friend Tor Bengtsson that what I'm describing now is machine psychology version 1, and I'm in my back of my head working on version 2. So I had mentioned quite briefly in the thesis something it's called interbehaviorism, which is let's call it another approach to the science of behavior.
Yeah.
And interbehaviorism is really a kind of behaviorism where you take all factors into account. And if I were to do this again, so to speak, and this is what me and Patrick and Tony are really talking about now, how can we integrate it with the interbehaviorist ideas? So in that kind of model, you have you can say unlimited amount of terms, and the critique that model has had in psychology is because it's not useful, people say, because it's so many models. But here, when you have control of all parameters, I think it can be extremely useful. So that's another type of term, and it's very easy to criticize our work from that perspective, because even in this case, when we had the dog there howling, my brother said that, no, I think there's other factors involved, like emotional factors, my history with the dog and the positive feelings that the dog has for me and whatever. It's so many factors involved there. So it's a bit naive of saying it can be described with 3 terms.
Well, that's both the strength and I think limitations of Skinner's theory, that as long as you accept his premises, it can't be wrong, in a sense. It's not testable in that way. Because,
it's not wrong, but I would say that he misses a lot of stuff.
Yeah, exactly. So the problem is not that it's wrong, but that it can't be wrong. It's defined in such a way that you can't criticize it from inside the theory, in a sense. You have to move outside. But anyway, it may still be useful. So moving on from that, if we then look at NAS, so there are many possible systems you could have used as a basis, and you mentioned briefly some other as well. Of course, you have all the traditional symbolic reasoning systems, and you have like formal logical systems and so on. a lot of cognitive models like SOAR or ACTAR that you mentioned as well. And then you have these AGI pretenders, at least. So why did you choose to work with NAS rather than something else? Given that you want to work within the symbolic tradition to start with.
So it's a good question. It was a strange coincidence that I heard about NAS. I mentioned to Pei Wang that it was something in NARS that drew me to his model, and he said something like, "It's always like that with NARS." That's, I think his interpretation is the only people who find NARS is the one who, you know, are attracted to something with the design. So I went to this campus and we had a lot of talk about, you know, behaviorism and stuff like that, and it was part of my flesh and blood, so to speak, and my worldview, and I saw NARS and it had these, you know, qualities of, yeah, that I described in the presentation. So it was something about it that felt right, but I don't say at all it's the only system. But I think Pei Wang's like brilliant insight of starting with the assumption of insufficient knowledge and resources. That's so extremely important. So, and Arne said to me when I had a version of the abstract that, "Oh, please don't write that this is an integration between learning psychology and NARS. It must be broader." So the text now reads adaptive computer systems. So then, what is an adaptive computer system? And one mechanistic idea is maybe it requires insufficient knowledge and resources to be adaptive. But it doesn't have to be, you know, we have changed, we only use a small part of NARS now. You can use JavaScript objects in terms of terms, or an even more brain-based control mechanism, something like that. It's a live discussion now. What really defines a NARS system?
So that's maybe a question for later, but I'll ask it now anyway. So when I think NARS has a lot of very attractive features, so I think it was a very good choice. But for me, if I try to do cognitive models, there's always the question of the degrees of freedom in the system or the model and the thing you're trying to explain. And of course, if you try to do general intelligence, then maybe you can have a very general system with many degrees of freedom. But one question would be whether NARS is maybe too powerful, whether it captures too many things, and because of that, is not able to find like the small solutions in a sense, and how much you have to work to get it to do what you want. And indeed, you didn't use all the functionality; you used parts of it. And would it work better or worse with everything included?
Extremely good question, and it would probably work worse. And this is a fact that my close colleague Patrick Hammer, he was totally ruthless. So he broke every assumption possible and implemented the system in his way. And it was meant for something for application purposes. But I think it turned out to be extremely compatible. The type of temporal and procedural learning that's there is so extremely compatible with how I view operant conditioning. So our work is really, I would say, when we started this work, we didn't have anything in 2021 when Patrick moved to Stockholm. We didn't have anything else than temporal relations, so to speak. So adding, for example, implications, that's an example of something that we took in from the original model. And functional equivalence and those kind of things is even more recent. And the last chapter on acquired relations, that's also an example of, if we were to put that in the system now, maybe everything would blow up in the sense that no test cases work, because it might be some overflows. It's an extremely careful approach to balance what to keep and so to speak. So even if we have one idea of the logic involved for the last chapter, it's an extremely hard problem to have that thing working together with everything that worked previously. Yeah.
Yeah, so that's a problem. I also struggle with complex models. As soon as you make any changes, you don't know it's all old things still work. And we're actually actively trying to work on that, so that once we do any changes, all the experiments are run again, and it's very easy to break things. I think that's an important thing to think about. One thing I really like what NAS is this idea about with the confidence of different things, and you have these two values, the number of presentations or whatever you call it, frequency and confidence. But is that sufficient? So I'm thinking about like some of my colleagues who work on reversal learning, for instance. Reversal learning, serial reversal. So you first train animals on something, and then you change it, and then you train it again, and then you change it back again, and so on. Training and then retraining or unlearning is certainly not the same thing as not doing anything at all. So I'm thinking about how that would work in NAS, where if you only have these values, when if you first, like, you have 10 positive instances and 10 negative, or you have every other one is positive, you get the same number, but it's not the same history.
Yeah.
So is that captured somewhere else?
It's captured by the frequency value will basically 0.5 rather than 1, if half of the cases are true. But the confidence will go up with more and more and more examples. And then the question becomes, what to do with this, or what's the purpose? And maybe you can answer that. So like, so what does the task consist of after that? So big, what to do with it?
No. So I'm actually thinking about change, where you have one. Say the outcome has changed. So you have, but this measure doesn't really capture the change. It's over all instances in a sense. And maybe it doesn't have to. I don't know, but maybe you see that, get that somewhere else.
So I don't understand this particular.
Okay. No, so say you think about it as like classical operant condition where you have a reward. And you can reward every time 10 times, and then you stop rewarding 10 times, or you can reward every second time. You get the same frequency, but what an animal does in that case is very, very different.
Some kind of reinforcement schedules.
Yeah, exactly. So it would be, for instance, it could be a reinforcement schedule, but also that you changes the contingencies halfway.
Yes. So I would assume that. So of course I'm familiar with the, let's call it the value.
Of course, yes,
But NARS can really capture this. So if it has, for example, learned one thing and gets reward half the time, and learns another thing and gets reward every time, the frequency would be higher. But if it's the same amount of, so to speak, events, the confidence, double frequency here compared to here, but same amount of confidence. So then in the decision-making scenario, a NAR system might, for example, choose something based on both the frequency and confidence. So it might prefer the thing where I got reward every time. So those are weighed together in the decision making.
Good. I think one could introduce a few extra values, but that's a different discussion. But maybe it's not necessary when you have a complete system. That's just looking at like one instance and outcome. Now I'll have a look at my phone. I probably just started. Let's see here. Yeah. About you mentioned that in your thesis also, that you could add like a perceptual system too, and as a starting point to show a picture of a cat and a dog or whatever. And then you get these symbolic discrete representations that you can work on. And you transform reality into this chess game. And you do it in a sense, if you look at the matching to sample examples and so on, it's like a game with pieces in different boxes, and of course you can do it differently, but you still have these fixed positions where you present things and so on. But how general is that? Can you always do this mapping from the real world to this kind of representations?
It's a very interesting question, I think, and in a sense, I would say that NARS take a bit more the approach of constructing the world rather than just like taking in the world. And so it's very flexible in the sense of it can have any type of, let's call it, sensors. Yeah. So if the only sensor I have is I don't know, black and white color detector, I'm not able to see all things that you can see or maybe can see. And you know, it's very, you know, related to the what is it like to be a bat question. That if you have some kind of sonar system, then you can observe the world in another way, or I would say construct the world in another way. So it is, of course, extremely limited, but it's at the same time extremely fascinating because of the progress in these technologies, the things that we can connect with Mars in a sense. And I think it's extremely fascinating to see all of these systems as potential, you know, subsystems of a robot or like it. I wouldn't see it as limited, and of course the system would, I would say, be able to do other things if it had a grid with more squares. Yeah. But I think the principles that we have tried to show, or that I have tried to show in this thesis, is possible to show still with these, let's call it, limited sensor systems. I think AI as a field, personally, I think has struggled more with these, you know, central principles of learning, adaptation, and that kind of stuff, rather than these kind of things that we talk about now. Yeah, but I know a lot of people will start with the perception side.
Yeah. Now, to someone like me who doesn't think perception and action is different things, it's kind of an arbitrary way to divide a system. But we can certainly do these things. So I mean, it makes sense to look at them. But to some extent, if you look at matching to sample and the different types of experiments you can do there, I mean, that's a way of transforming a continuous messy world into something that is very discrete and symbolic, and in many cases see what animals can do there. And not all of it, but some of it came from the idea of trying to train language to animals. So there you had this idea, let's make the world more like more linguistic, more symbolic, and see if animal can learn that. And of course, it doesn't go very well most of the times, but humans are really good at it, and it probably has something to do with language. But if we move on to this empirical work here, you have you looked at sort of a standard or more cognitive, if we can call them, than matching to sample experiments. So if we start with sort of the identity matching experiments, and it's kind of fun because it looks so trivial because we're so good at it. We don't even realize it is a problem. It's not a problem until you try to train animals to do it. It turns out that they can't. But there, I'm not so sure whether we actually need to. Here, the system is not really trained because it's not really iterated training in that way, but it learns from experience to do this, and most animals seems to never do it in a general sense. But all humans do it. But do we do it after training or without training? That's the question, because even infants can do this. And even if you haven't specifically trained them to do it. So I wonder again, whether is this too powerful because you can learn it? Do we have to learn it? I mean, it's outside of physics, but you have to ask anyway.
Yeah. So I think I answer your question if I say that one take-home message of contemporary learning theory is that once you acquire language and the ability to do this arbitrarily applicable relational responding, that transforms all learning processes. And what does that mean? It means that even classical conditioning is affected by these processes. Yeah. So for example, if I show to you two events close in time, which would be a classical conditioning, it might better be explained by symbolic reasoning. How they probably have a relation because they were close in time. And to answer your question, do people do this or like identity matching? Probably not as much because it, like symbolic and verbal processes, has taken over or at least have transformed all these. But one, I think, take-home message is that maybe it's not identity matching in itself that is the important, but rather from a mechanistic computer science perspective, maybe we need some kind of abstraction, or some people will argue for variable introductions. Some of my Mars colleagues argue for models without that.
Yeah.
But from a learning psychology perspective, we need something that Jan de Hago would call effects on meta-regularities to explain those things, and what RFT people call generalized operant behavior. That seems to be very, very necessary. So the mechanisms that I tried to talk about in that chapter is meant to enable that, so to speak.
Yeah, so I'm not, we shouldn't go back, but this is similar to the concept of a Saussurean sign in semiotics, and I don't want to go there, but anyway, there you have this almost identity between the say this the token and whatever it refers to, where you can go both ways. But it's almost like identity, but it's not the same thing. So, I mean, if you have a dog and I name it dog, the word dog and the dog is not the same thing. So even if I can go both ways, it's not the same thing. They are sort of symmetrically related, but not identical. So I wonder if that's something that matters to this kind of.
Yeah, absolutely. So you're basically asking the fact that human beings, for example, so early can relate to the real dog and the word dog or the sound dog as the same thing. So absolutely, that's like I would say almost the most important thing here, that how to explain that fact. And we know that we can train a dog or something, but then we need to train in all directions.
Yeah, no, exactly.
So the question is, how can we then have a system where we only need to train, how to say, part of the relational network, and it can derive the other parts? So that's exactly what RFT is about. So what history is needed for the organism to be able to do those kind of derivations? That's what we mean multiple example training. But if I take one step back, when we talk about functional equivalence, it is already there one way to, let's say that if I learn to do some operation with a dog and the same operation with the word dog, functional equivalence would be to relate as those two as substitutable in one sense. So on one level, that's kind of what some animals could do. But to have the real flexibility of this relating, I think we need something more powerful, which is the content of the last chapter.
No, I think also you call it general identity matching, but if it's not general, is it identity in that case? Isn't it just conditional responding? Or does general add anything here?
Yeah, I agree. And generalized thing,
or generalized
in new situations that I haven't seen before.
Yeah.
But I agree the name is not super good.
No, because I haven't seen that before. Just typical general. Now, if you look at always like learning symmetry, also that again is something that infants they get that immediately. But that's one thing you don't talk very much explicitly. I think it's in there, but that's learning transitive relations, and that's fascinating because all animals can do transitivity. But not all humans or small children don't always get it, which is surprising because I mean we do it when we're older. But that's actually something that seems to be easier for animals than for humans, and I'm not sure why. But you don't test that here, and I would just would have expected that to be one of your examples. Is it intentional or maybe not? It's not necessary here.
It's extremely fascinating question, I think, and very difficult because. So one example is that when when they for the first time with RFT under extremely controlled conditions found an infant who could not do symmetry, and they were able to train it with multiple example training to develop symmetry. The child spontaneously did transitivity without explicit training.
Okay.
And if I remember correctly, with the sea lion study, they did not train transitivity explicitly, but it is a problem with these studies because, how to say, I think it's important to make a distinction between transitivity as on observed performance in a test and some kind of learned relation.
Absolutely.
And as I see it, as people typically have arranged these tests, or you could call it stimulus equivalence and that kind of stuff in the animal literature, our model can explain that with functional equivalence. So our model would do what they call transitivity without explicit training, with just combining things. But to really learn transitivity, like seeing it as a pattern and then taking it to a new situation. This research that I have presented suggests that the mechanisms in the last chapters are needed. So it would suggest that animals can learn transitivity in that sense.
So in a sense, explicitly you're using it, and maybe when I said most animals get transitivity, it's not always in this sort of explicit sense. It's just the way we respond in such a way that it looks like they grasp the concepts, but of course we don't know what happens.
Yeah.
Going back to my phone again. It's a fishing expedition here to find something. Yeah, some more concepts I didn't see in your thesis, but I expected initially, and that's things like I mean, in cognitive neuroscience, people talk about like behavioral sets or cognitive sets and mechanisms like contextual inhibition and things like that. Task switching, for instance, but seem to be very related to relational frames and what you're doing here, but you don't mention them. I would like to hear your thoughts about that.
And a lot of people, including me, agrees in the Norse research community agrees that inhibition should probably be more explicitly there, so to speak.
Yeah. So
if we were to do the Wisconsin card sort of
for instance,
North, it would, I think, fail. So that's one very good example of, I didn't mention that, but Tony Lofthouse control model is extremely much inspired by neuroscience. So I think it's there where all this neuroscientific knowledge can really be in there, and inhibition is a concept that belongs there, so to speak. How can NAR, so to speak, inhibit itself from doing something?
And it's actually related also to a question before about changing, reversing earlier learning and so on, whether you forget something or whether you inhibit it and do something else. And one reason why I is interested in this is that when I try to model these things, similar experiments, with contextual inhibition is a very central part of it. So one thing is like learning the positive behaviors, and then you have to learn separately to refrain from doing something else, and what's the result is when some can be, for instance, identity matching or matching to samples. So I think it has a place for it here, even though I mean, a lot of psychologists that swear that inhibition doesn't exist. So if you only look at like a true behaviorist at behavior and frequencies and so on, then there's no room for inhibition, but I think it's needed.
Absolutely.
So I have some final questions, and I think I will leave some space for the thesis committee. Yeah, two general things. I reacted to the term motor babbling or babbling here, and the reason is that it's used usually in like infant learning and so on, but you use it, I think, for trial and error. But if you look at motor babbling, for instance, in infants, it's not trial and random search. It's goal directed.
Yes.
So classic example, if you see a baby moving its hand like this, it looks random. And you have an object here. But if you look at it over time, you can see that it's much more in the direction of object than anything else. So it's actually trying to reach for something. It's just very bad at it. So it's not really searching randomly. So I assume you use it as a synonym to trial and error. But correct me if I'm wrong.
Yeah, but it's excellent that you say this, because it's so true that NARS, as we have done here, it doesn't have motivation systems. So the dog in the movie, for example, you can argue that it has some kind of play system. So I think one way to look at it is that we have these, let's call it inborn motivation systems that for various reasons, genetic reasons, makes us do various things. And human beings have the attachment system, which motivates us to do a lot of things. So I think motor babbling is just one, let's call it, shortcut in the sense that we don't have these motivation systems. Yes. But I would say, on the other hand, that at least a motivation system or motor babbling is needed to kickstart responding so the learning can take place.
No, I agree on that. So final question about general systems. When you look at things in this sort of very abstract sense, and for instance, matching to sample was considered for a long time to be something very complicated, but only a few advanced animals could do. And many people thought that this is something that shows that you're really clever if you can do that. And of course, you can use matching to sample paradigm to study all the things you write about in your thesis. But then a few years back, someone showed that honeybees can do matching to sample, which was quite unexpected in a sense. So then you can draw the conclusion, because if you look at this as an abstract problem, then they can do it just as well as like a chimpanzee, for instance. But they can only do it if the stimulus is a color and the action is flying through a little hole. And they apparently can't do it in our context. So formally, they can do it. But in reality, they can only do it in very limited circumstances. And what I'm a bit afraid of is when you look at problems abstractly, like this, I'm not sure whether you're building a bee or a human. So, like, your final thoughts about that?
So I'm trying to find an example. So maybe the other thing you said is that you said 20 minutes ago that it's very limited to have this square thing. So in a way, it's a bit similar to that some animals have this very limited response systems. But it's very, very true that, and it's covered by, I would say, Jan Hauer's way of looking at like learning, that this is what he would call moderators of learning, that the kind of response is important, the kind of organism is important. And so if we are building a honeybee or a human being, I would say that generally NARS is not very limited in this sense. So I would assume it moves towards the human being. And of course, in this context, when we talk about AGI and human-like AI, I didn't say that, but I think that's a good term, human-like AI. I know that you in Swedish have been talking about en mänskligt baserad AI. I think you could translate it to human-like AI. So human-like, I think definitely that what we try to do with our work is to create human-like AI in that sense, even if it's a totally different body, but same on a principle level and not too restricted, as for example the honeybee.
Okay, so with that, I thank you very much.
Thank you so much.
Great discussion.
Great. Thank you very much. Thank you.
And I will now invite the graduation committee to start their questioning of Robert, if they still have any questions after Christian's examination here. So I would like to start with Professor Gordana, which is online. I hope we can hear you.
Yes, I hope.
Yes, we can. So I invite you to begin with your questions to Robert. Thank you.
Okay, thank you so much. I'm really glad to have got this opportunity to read this very, very stimulating and interesting work. And it was the first time I met NARS and those ideas, which are really so fresh and exciting. So I would like to know, how scalable is machine psychology for complex real-world application? How do you imagine to combine this with existing approaches?
So I know of your interests of modeling the whole universe. So I'm curious if your question comes from that perspective.
Actually, I was thinking this LLM approach, which is so powerful, I can imagine it may be combined with your approach. Also, cognitive computing, for example, in the same framework. So do you see possibilities to combine?
So short answer, absolutely yes. And to start with, how to combine NARS with LLMs, I would say it's quite similar to how we talked about these pre-trained models like object classifiers. So you can see an LLM almost like, how to say it, response in the biological sense. Patrick has done some preliminary work of integrating NARS with GPT. So it's the general idea is simply to how to say it, pass the entire NARS memory as part of the prompt back and forth. So NARS can then act as the long-term memory to an LLM. So it basically, in interaction with a human being, with an LLM, the system could learn and maybe also derive things using the NARS rules. So I think personally it's an extremely exciting way to move forward, because in any application that we want to use, for example, my own use case, maybe I'm interested in creating a virtual patient in psychotherapy. It's already now possible to do excellent things with the GPT, but combining it with NARS would potentially create a whole new functionality. But I think regarding your first part of the question, how much it can scale and so on, I think it is by design really meant for ontogenetic adaptation, in the sense of, as I see psychology, it's defined on the whole organism as its limits, so to speak. And I wouldn't use one NARS system to model a group, for example, or the entire universe. But it would, on the other hand, be extremely possible to use like multiple individuals or organisms and study that system with multiple NARS systems. On the other hand, I for some reason, I have the intuition that you're aware of these, I don't know, Buddhist models of the mind. And some of them are, you know, systems of systems and systems, so to speak. That is actually very compatible with how we also envision a future NARS system, that, for example, the different sensory systems can, how to say it, be NARS systems in themselves. So one organism is a collection of multiple NARS systems. So that would be maybe one solution to adaptive perception, to have a NARS system on the vision system. But generally, yeah, I think I at least has touched on your question.
Absolutely, it was an excellent response. Thank you so much.
Thank you.
Do you have any further questions?
Do you want me to ask all the questions I have? I have a long list.
No, no, I just want to make sure that we're not missing out something. If not, then I will hand over to Professor Strannegård and to ask to Robert.
Maybe I can, yeah, I can ask them.
Can you hear us now?
Är den på mute?
Ja.
Den
Nu är din.
Men vi kör bara
Nu kommer ju micken är...
Okej, så jag står och pratar så här nu va?
Och
Okej,
du kan stå.
då lägger jag bort den lite. So, can you hear me now, Gordana and Antonio? Okay, great. Yeah, so I'm interested in to hear a little bit about NARS. So I think that it's not exactly logic, like an abstract logic with a Tarski semantics, doesn't qualify to that definition. It's not exactly a probabilistic logic, not exactly a belief revision system, not exactly a non-monotonic logic, but it is a term logic. It uses a copular relation, but that's not very informative. It's just one small feature. And so I think it's more like some kind of rule-based system for learning and reasoning. And trying to take it a little bit further, I think there are some quite clear similarities with inductive logic programming. So in inductive logic programming, you have these examples and a number of counterexamples, and then you are looking for a hypothesis that will enable you to derive all the examples and none of the counterexamples together with a background theory. So I think that is something that is also used in NARS. And that is interesting because inductive logic programming is like a symbolic system that uses observed data for updating all the time the hypothesis. So it uses it's a symbolic system, but it uses a simple form of supervised learning. And before you said that NARS is neither symbolic nor machine learning. But I think maybe it would be possible to claim the opposite and say that, well, actually NARS is both of those, because you do have this symbolic component and you do have an element of learning from data. So do you think it would be fair to say that NARS is similar to this setup, the inductive logic programming? With the important added idea of frequency and confidence.
So I think it was Sam Tellman who pointed out that the first time to me that at the coin seminar that the real power I understood of the inductive derivations, it's really the key to everything like here, like the one-shot learning and the building of these learned contingency. So the inductive derivations are extremely key. Yeah. Yes.
Okay.
And in a way, the sensory motor reasoning, the temporal induction and the goal deduction combined, they provide a way really for NARS to, you know, interact with the environment to, for example, play Pong or tasks like that.
Yeah.
So in a way, I agree with what you're saying.
Okay. And so I'm also interested to understand how NARS compares to other like potential AGI systems, and of course ChatGPT comes to mind. And like you said, like well, no, humans and animals are pre-trained by evolution and by life, but we are also capable of ontogenetic adaptation or learning. So we can do both. And what about ChatGPT? Well, it's also pre-trained, and it can already at the beginning answer a huge amount of questions and so on with zero additional training. But a thing about ChatGPT is, of course, that it can also do ontogenetic learning. So it has a memory that can enables it without ever changing the weights or the parameters of the neural network. So you have this possibility, and I entertain myself by trying to see what ChatGPT can do on the tasks that you have in your thesis. So I just fed it with simple information, like, for example, red triangle, blue square for the match to sample test. And then it answers something, and then I just said right or wrong, and it picked that up immediately. So that was no big deal at all for it. So, and the same thing happened with operant conditioning in a generalized form. So identity learning also in a generalized form. And then this relational responding, your clap or wave example, did that too. And also choosing the largest, that was immediate, more or less. So ChatGPT can do both. It is pre-trained, but it can still do these things, adapt and learn very fast. So I think that this suggests that large language models can give NARS a match also at ontogenetic learning and at emulating human and animal behavior. So my question is, how would you compare NARS and LLMs from the perspective of AGI?
Very good question. And yes, it's personally, I think that when it comes to memory, I would say that the kind of memory that ChatGPT, for example, use, I would call it more like an array. It just feeds information. And the other day when I used it, it said, "Oh, my memory is full. I will now start to remove things." So I wouldn't even call it a memory in a sense. So personally, I think that GPT struggles with the ontogenetic part, but it's so impressive with the other parts. So it can really look like, how to say it, very advanced behaviors. And of course, it's a very important task for researchers to come up with tasks that maybe are very hard for one or the other of the models, for example.
Yeah.
Personally, my interests are really not in the domain of trying to use GPT for these tasks.
No, I can understand that. And one reason could also be that NARS is much more transparent, whereas ChatGPT is completely intransparent.
Sure, yes.
So that's getting back to that, but that's one of the big differences. But I think it's interesting to note that ChatGPT can also solve these many of these tasks. I didn't check all of them, but okay. And then another like competitor would be the deep reinforcement learning when it comes to modeling animal and human behavior. So deep reinforcement learning agents, they can operate both in lab environments and in ecosystem environments, more realistic ones. And I think that, so now we have seen that NARS models work well for the lab environment. But yeah, do you think they could also work to drive animals in like ecosystem situations? I think.
Yes. So before going to ecosystems, Patrick Hammer has done extremely great work of putting NARS on a real robot operating in the real world.
Yeah.
So the first paper we had on that was, driving around in the Digital Futures building.
Yeah.
But the latest paper that it was accepted to this top robotic conference, ICRA, that's really, going down to Denmark where they have this robot lane in Aarhus. That's really where you have to deal with the real stuff like sunshines and all of that stuff affects the performance.
Yeah.
So I'm impressed by what NARS can do there. Yeah. But of course, it's far away from being a real animal running around at that island that you model in Gothenburg.
No, yeah. But one thing that would maybe need to be modified a bit is the reward system, because then you would have to reward it for staying alive, and rather than just giving it like 1 point per berry that it eats or something like that.
Mm-hmm.
And then you would also need to pre-train it, I think, so that you can put it into a new environment and then it will have a chance of surviving there without having to learn everything from scratch.
I agree that also related to Christian's questions on motivation systems. Like if we're doing this kind of animal, it needs to basically, as I said, have some kind of fear system and the need to reproduce and things like that. Exactly.
Okay, and then a question about relational frame theory, which I'm not very familiar with, but so it's a theory, behavioral theory of human language. So why is it good to use it for modeling animal behavior? I mean, it's just there's no contradiction, but is it a natural choice?
So I'm a bit aware that I have been sometimes maybe a bit vague in my descriptions where I write functional learning psychology and RFT. So to be technically correct, I would say, I'm very aware that this has not been very clear, that it's the before RFT things that we use to model animal behaviors. It's when it comes to symmetry and so on that we really make use of RFT.
Yeah, okay, I see. And then brings us to my second question. Why this obsession with symmetry? I mean, nature is full of relations. Some of them are symmetric, some are not. But why are they only looking at symmetric relations, or even assuming that all relations are symmetric?
Great question. And personally, I think it's the first real building block to symbolic cognition. As Christian asked about this substitutability between the real dog and the word dog, for example. Substitutability in itself, as we mean in language, is symmetric in that sense. But I agree with you that nature is full of other
yeah. But of course, I mean, if you use substitution, then you have to be sure that there's some kind of equivalence going both ways. Yeah, that I can understand. Okay, and then machine psychology. So I think you are more or less introducing this concept, and it's a very good and attractive concept, I must say. But you use it in a very specific sense. You talk about an approach to AGI, which is based on NARS plus RFT, which is a super narrow definition compared to what it could have been. I mean, you could have said that, well, this is an approach to AGI that uses methods from clinical psychology to explore machine behavior, both intelligence and personality. Something like that. I mean, the idea isn't bound to NARS or to RFT, or do you think so?
So we touched a bit about this with Christian, that I think it's it's the science of ontogenetic adaptation.
Yeah.
It's an approach to psychology. It can be even broader, and we talk about this interbehaviorism framework. So that's the psychology. And it doesn't have to be NARS, but I would argue that it needs to be some kind of adaptive system.
Adaptive, yeah.
So
Yeah, absolutely.
adaptive computer system.
Yes. So I think the approach, well, first of all, it's not completely new because it began with already Turing and the Turing test and Newell and Bringsfjord. Now the people have worked on this this idea of putting the system, viewing the system as a kind of patient that you can make experiments on. But I think it's a very important thing because if we imagine that we want an AI system to do a particular job, then we need to know that it's intelligent enough to do the job and also reliable enough to do the job. So, I mean, also the personality of the system matters a lot. Whether can we trust it? Does it have any like psychopathic traits, for example? We don't want that, right? So we need to be able to trust an AI system. We need to know some things about its like mental faculties, not only its intelligence, so that it can actually do the job, but also its reliability. So I think it is something that is super important when we are going to like deploy AI systems. Okay. And then another thing is explainability. So now you're using NARS and the transparency of NARS to study like psychological mechanisms, which mechanisms are sufficient for creating certain types of behavior, for example. And I think that's a very important thing. And it would be hard or impossible to do it with like neural network-based systems because they are like black box models. So that's a big advantage. But on the other hand, maybe the black box models can make really good predictions. So there is a trade-off there, maybe. I mean, a great advantage of NARS is the transparency, but whereas maybe other models are really good at making predictions, for example, about the next thing that a person will say or something. So there's this trade-off, don't you?
Yeah,
don't you agree?
as you also highlighted, the NARS can be seen as data-driven in the sense. And let's say that we have trained the system to, it has been part of a lot of conversations. We can expect the system then to do predictions about what happens next. That's part of what NARS can do.
Yeah.
And it's possible to also update those predictions based on what happens. So I would argue that it's a bit of it is really there.
So if you're interested in psychology, then this transparency is very important. But if you're interested in AGI, maybe less important.
You mean transparency in the sense of explainability?
Yeah.
I think it belongs to AGI, really. The explainability. I think it's a great... Also asking the question what to do with AGI when we have it.
Yeah, okay. Yeah, of course, it's good to have. I can agree with that. Okay, and then I think the final question here is about the tasks. So you looked at a number of psychological tasks in the thesis. And of course, from the AI perspective, it's a very small corner of the whole problem space. But from the psychological perspective, I think it's like an important set of problems that you looked at. And NARS did well on them, I think. And yeah, I'm sure that NARS can also solve many more psychological tasks. For example, like progressive matrices, things like that. And many psychological tasks, they can be framed in a way similar to this one, like as problems in small grid worlds, where the agents make choices, like with a joystick. And yeah, so then you could create use one and the same NARS agents for many of these problems in grid worlds. So you could have a fixed NARS agent with a fixed like set of observations, like fixed observation space and action space. and then you could train it, and then it could do many of those tasks without any need for like restarting or anything like that. Everything would take place in the same world. So I think, do you think that would be possible, and would it be interesting potentially?
Yes. So there is a very recent NARS system. I haven't been part of it, but it was published at the latest AGI conference. It's called, you might remember Derek Cook from, we had dinner in Prague, and people were making jokes about this person who worked as a pawnbroker. Oh, that's what Einstein did to fund his research.
Yeah.
So this guy, he has invented this extremely nice system that Patrick Hammer has combined with NARS. So this system, NACE, is exactly what you say, that it's extremely much a grid world, but that enables the system to, for example, have much longer contingencies, because there's, how to say it, everything is so fixed. So a lot of the assumptions from those worlds can be combined with NARS. So it leads to impressive behavior, extremely impressive in the grid world, like it can solve tasks that I can solve. So that's an important step, I think. And another part of that model is that it models curiosity in a sense that I think is very interesting. So I wouldn't say that's necessarily the path to AGI, but extremely inspiring. How can such a system with those restricted assumptions do these impressive things? It's inspiring for also other research.
Absolutely. Okay, thanks very much.
Thank you very much.
Your answers.
So let's see if you can hear me. I think we will continue with Professor Antonio, and then we will switch back finally to Gordana if you have any final questions. So Antonio.
Okay. Yes, here I am. So, hi, Robert. So thank you very much for this very interesting and intriguing thesis. Many of the questions have been made by Christian, and what I would like to know is what is missing, in your opinion, to implement such a system in a robot? Because I know that OpenNARS for application was the main idea was to implement NARS in a robot, in a system. So in order also to consider the embodiment aspects of this, the embodiment aspect of AGI. So what are the steps, in your opinion, that are missing in order to implement your systems in a real robot?
So I would, in a way, say nothing. If we wait with the last chapter, so I think it's a perfect research project to take, for example, chapter 6, 7, 8, and basically have it run on one of these robots that we have been using. And as you highlight, the embodiment aspect will be very evident then, for example, because such an easy thing as gripping a square, or is it a cube, and lift it up, it's okay. We can then use the pre-trained model that the robots comes with to pick it up, or it can be something that we do more adaptive, like really making the system with trial and error being able to pick up the cube. So to answer your question, I think a lot can be done by combining the software that the robots comes with NARS, but to have it even more adaptive in the sense that I think you're interested in is a harder problem that I think requires the system to be a bit extended, maybe, in how we look at also the representations that the system learns. So, for example, if the spot robot dog can be controlled by, moving to locations, it's a challenge on how to integrate all of these parameters that you feed there with the reasoning process. But I think the architecture is there really to do it.
Yes, no, I essentially agree with you. No, I have two more curiosities. The first one is that you essentially you have not considered the role of emotions, the role of motivation. So these aspects of psychology, which are relevant in the AGI literature, and even you don't consider the more high level systems like the introspection, for example. So you pose your psychology experiments in a sort of middle level. So maybe what do you think you can integrate aspects from the lower side, from the emotional and motivation? We also have Christian Balkenius that worked a lot on the motivational emotions. And on the other side, on the fact of more related to introspection, self aspects, and whatever. Just a curiosity.
So I know the work that you have been doing on the robots with introspection, for example, and I think that's extremely fascinating, and it's also a good, so to speak, test for the psychology theory that we use, how to talk about introspection using a behavioral psychology model. That's also, by the way, an example where we briefly mentioned these interbehaviorist theories. It's easier to talk about that there, but it's how to say it? It's a challenge to approach these things that you mentioned and still stay coherent with a theoretical framework. But emotions, of course, and once again, so NARS had some kind of emotion model. There is more recent work that Pei Wang is doing in his group. I think there's a lot of exciting work that needs to be done, like integrating NARS even more with an emotion model. And the thing I mentioned with the curiosity is one dimension of it. But yeah, I can only say that I agree about the importance of it.
Okay, thank you very much.
Thank you.
Gordana, have any additional questions?
Okay, I have two small questions in the end. The one is, do you see a possibility to involve ethical aspects? Because
Ethical
Antonio
aspects?
was mentioning already things connected. Do you see possibilities?
Absolutely. And I think to really, how to say it, make that very clear, I would say that systems that learn with ontogenetic adaptation, they are both, how to say it, excellent for doing ethical AI. And maybe it's the only path forward to do really ethical AI. Basically, it means that we have control over the schools that the system take part of, that learns the values that we have, so to speak. I really, how to say it, believe that should be the guiding star of this type of research.
Yes, thank you very much. That was what I was thinking all the time, talking about transparency and need to understand.
Now you sound, let's see what happens. Now we hear you again.
Okay, so my last question is, working so interdisciplinary, cross-disciplinary, and collaborating so much across all the boundaries and so on, what are your experiences?
Only positive. No, but to be honest, I think the biggest challenge has always been this thing that I have some, let's call it, own definition or intuition about what I mean with learning and from the behavioral psychology. that we describe it with functional relations. It can be a challenge to interact then with people who view things extremely differently, that it has to be a structure, for example. So that has been part of the challenges. It's extremely common. I hear it almost every day that people refer to human beings as if they are a computer. We use terms all the time that we have taken from computer language and use it with people, and we assume that people work like that way. So also I think behavioral psychology and RFT takes another approach, that we work like animals, and it's about adaptation. That's the language that we want to build on. So sometimes it can be a bit, two different worlds. But I think these ideas get more and more also common, that adaptation should be at the core, for example.
Thank you very much.
Thank you.
Thank you. Is there any other last questions from the graduation?